I don't know yet. We'll see. Anyway, okay. Hello, everybody. I think we should be good here in a second. Um, so sorry about running a little bit late here. We got caught up at work. Somebody brought in a second uh, chessboard, so we were playing Bughouse chess, and that was interesting. So let's see here. This past weekend was ASIS CTF, which was put on by the ASIS group. And let's see if I can pull this up. So ASIS CTF, this is acting a little slow. Do I have stuff running? Firefox is being dumb. Okay. You can go away. Right, so let me just check here. So yeah, ASIS CTF was this past weekend. And tonight, we're going to be talking about some of the ponables from it. Hopefully, almost all the ponables, but we'll see how far we get through in the time we have. So, first off, let's go take a look at ASIS CTF. So, first off, ASIS CTF was... Come on. I guess that was not the only thing that was being slow about my machine. I must have something else still running. Oh, we can live with it being a little bit slow. The good news is that what we're doing tonight is not super resource intensive. So, right. So ASIS CTF. So ASIS CTF is put on by the ASIS group. I know that I've followed several of them on Twitter. If you follow me, you can also follow them. But I don't actually know much about the group other than that they've put on ASIS CTF for the past several years. So, as far as things go, they had a pretty good selection of challenges this year. Just pulling it up right here. I don't know how many of these are still up. I do know that at least as of this morning, I could log in and view them. But, ooh, this is not happy. Here we go. My Firefox in this VM is not happy at all. Well, anyway, so they had several challenges. It looks like there was a really strong competition, and that basically the top several teams, looks like both of the top teams. Okay, so it looks like the top team cleared the board except for one challenge that nobody solved. The next several places are just a couple of challenges that they didn't solve, and we were way down here on like a couple pages in. So, but talking about the things that did happen, they had a pretty good selection of challenges. Actually, let's see here real quick. Are these still up? Come on. So one thing that they did that I've noticed has been coming up more and more is that they'll have... Oh, yeah. So it looks like challenges are still up if people want to have a try at them. But what I was saying is, one thing that I've noticed in ASIS CTF and that I've noticed in several CTFs is that they'll have a description and they'll have a link in the description. And while that works reasonably well, the color matters a lot for that. If I haven't clicked on one of those links, where's a good example here? Tatter. Right, so this probably, yeah, like if I haven't clicked on this link yet, on my monitor, those look exactly the same to me as the rest of the text. So I have to actually take my mouse through here and see where it changes, or I'm gonna have to inspect the element and figure out where it changes. But yeah, personally, not a huge fan of the links being in line with the description just because it's harder to see. I know there was at least one of these challenges, I think it was random generator maybe, where I open it up, it says, okay, it's running here. I didn't catch the link. So I'm sitting here poking at the service for probably 2 or 3 minutes before I go back and take a look at it again and go, oh, no, there totally is a binary there that I need to look at. So just a personal pet peeve that I'm not a fan of that because it's harder to see. And if it's harder to see, it's just, it makes it difficult, but not for interesting reasons. So With that said, let's talk about some actual challenges. So they had a relatively robust set of ponables. As you can see here, they had 1, 2, 3, 4, 5, 6, 7, 8 ponables, of which we solved 4 of them during the competition. The plan right now is that we're going to run through real quick, start and start hard, followed by CRC and foo interpreter. Those should be pretty quick to run through and talk through. And after that, we're going to solve the Kanak MGF and Kanak MGF remastered, hopefully live, because I spent probably way too much time on them during the competition, only to realize as soon as somebody posted a write-up in the IRC what I was doing wrong, and we should be able to fix that pretty quickly and work through them live. So, with that said, we should probably also say a few more things, which is that, come on, FitHack is currently running, as is Pico CTF. Both of these are relatively low difficulty challenge competitions. So if you're looking for something to practice or something to just poke at, I know on Sunday, because ASIS CTF ended Sunday morning my time, I had all afternoon Sunday to play. So I poked at the FitHack CTF for a while, and I thought it was, for very low difficulty challenges, they were fairly amusing. Like they've got an entire category of RE challenges that are probably 500 to 200 point challenges, or 50 to 200 point challenges on the normalish scale. So very doable for basically any skill coming in skill level. Also poked at a few others. The web challenges are fairly decent. They've got a couple PCAPs to look through, some forensic stuff. I took a very brief look at the crypto stuff. I think I only really looked at one of them. But yeah, definitely take a look at that. Definitely take a look at the Pico CTF, which isn't here, but is apparently up and running. I believe it's supposed to be run by, it's intended for middle school and high school students. I don't know if they allow anybody to register. Yeah. But in any case, check those out if you want something low difficulty to play through. They should be good. Also, this coming weekend is going to be BCTF, which, again, I expect to be a ton of fun. I'm definitely looking forward to it, and we'll probably spend a good chunk of the weekend playing. There's also a couple in-person ones. I don't remember who qualified for RUCTF, but that should be, at the very least, there should be some entertaining results coming out of it. And there's apparently a hack-in-the-box one going on now if you just happen to be in Amsterdam, either for the conference or because you live in Amsterdam or just visited for some reason. But that's this coming week of CTFs. One thing worth noting is that I will not be streaming next week. I've been doing these weekly, and next week I'm going to be on vacation and will not have internet access all week. So, next week's stream, there's not going to be much going on for me, although I do know that Ginvale is streaming Wednesdays in the afternoon my time. Definitely worth taking a look at. Let's pull that up real quick for people. Yeah, I don't know what is so unhappy with this. Come on. But yeah, Ginvale streams every day. I think it's apparently Wednesday at 8 p.m. his time. I believe it's 2 p.m. Eastern, so mid-afternoon for people in the U.S. But I believe that this week's is supposed to be talking about some kernel exploitation stuff on the Linux kernel. So if you're looking for something to watch, definitely recommend checking out Ginvale's stream this week. Or next week. This week and next week, because apparently it's going to be a two-parter. But yeah, so next week I'm going to be out. Also, Wednesday I'll be streaming. If you missed it last week, On Wednesdays, so the plan going forward is that Mondays I'll be talking about CTF stuff because for most weekends there was a CTF the previous weekend that I can talk about challenges from. And then Wednesdays are going to be looking for real bugs. And real bugs are being just some real piece of software that does not intentionally have bugs put in it for the purpose of finding them. Because that's one of the classic points a lot of people like to make about CTF stuff, is that CTF isn't real. The bugs are placed there intentionally. It's a different process. So Mondays, I'm looking at CTF stuff on stream, and on Wednesdays, we're going to be looking at real stuff on stream. We started with PDF Crack, which is a piece of software from almost a decade ago for brute forcing PDF passwords. Currently, we have heap corruption from that. We fuzzed it for a while on stream with AFL. I've had that same fuzzer running for the past week, so I haven't gotten a chance yet to take a look at if there are new crashes. But we currently have heap corruption, and the plan is to land that with a little bit of cheating to make it easier, but unfortunately means that never going to be a high-risk bug. But we're going to land that on Wednesday, and then I think the next thing going forward is going to be looking at some Python parsing things. So looking at some Python modules and seeing if we can find some bugs in some of those. So that's going to be Wednesday. This week, next week, it'll be canceled like both streams. But this Wednesday, 7 p.m. Eastern, we'll be looking at PDF Crack and then Python. So with that said, let's take a look at some challenges from ASIS CTF. So looking at these, there's several of them. I have them pulled down here. Let's start with Start. So Start was their initial challenge, their what did they call it? Warm-up pwnable. So let's open it. If we open it up, it's super simple. You can see the fit hack ones that I opened up already. But for Start, which of these do I want? Oh, I want this one. The other one's an IDA database. So super, super, super simple. All the binary does is it calls read onto the stack with a way larger size than there is space on the stack. So if we do python-c print a times, we said it was 400 hex bytes? 400 hex bytes, yep. 400 hex bytes into /start segmentation fault. I need to turn this on, ulimit-c unlimited. This is turning on core dumps because I don't have it set up in my shell to automatically do this. And how things are configured. So there's ulimit, which sets the limit for various things on your system. The -c is for the core file size. On a lot of systems, the default is 0 bytes, which means it will never write a core file if something crashes. By doing ulimit-c unlimited, it will write out a core file if something crashes. Some of the other things that are sometimes relevant, most of them aren't, but I have seen people use stack size a couple times, as well as doing things like signals I've seen once or twice. I think that's messing with open files I've also seen. But for the most part, it's ulimit-c unlimited to turn on core dumps. So that's what that is. You also have to remove the previous core because by default, it will not overwrite an existing core file. You can change the core filter, which is a format to save new core dumps as. But we do this and we go, oh look, we have a new core dump. GDB start core. That looks like good register state. We do a x/x $RSP, and we want a double word, quad word, right? Quad word. We want a quad word. And we see, oh, look, it's a whole bunch of lowercase a's, which is exactly what we threw in here. This is just a super simple ROP chain. If we take a look at the exploit that I threw at this, exploit is kind of a loose term here. Basically, I'm just using pwn tools to put some bytes in to pad us out to the first return. The first gadget I'm using, this output right here is just from, and let's do this properly, screen start, no, I want to open exploit. So that output there is from pwn tools, or not pwn tools, ROP gadget. And ROP gadget is a tool by Jonathan Salwan, I think. And I always forget. So ROP gadget and checksec both have a flag to specify what file to give it. I always forget which one is which. One of them is file, one of them is binary. Although apparently I called it right this time. So anyway, these comments here are just the gadgets out of this. I dumped them to a gadget file, and you're seeing the line number out of that file, and then the gadget. So this is a pop RSI pop R15 because I need to. So what I'm doing here is I'm loading the arguments to another call to read, and then we're going to call read, and then we're going to give it some shellcode, and then we're going to return into our shellcode because NX is turned off on this binary. So tools checksec. It was binary for that one, so it's file for this. So yeah, NX is turned off. We just throw some data into the BSS, and we're good. Yeah, so what we're doing here is we're loading the registers for a read call. So this is read. We need RDI to be the address we want to go to. I'm sorry, we want RSI to be that address. RDI needs to be 0, which it still is at the time of the crash. So if we do gdb start core, we can see RDI is 0, so and RDX is 400. So if we set, so RSI is going to be the second argument to read, which is the buffer that it fills. So we just give it address. This is in the BSS someplace. I think it's after all the variables, but I don't remember. But we throw it in there. We then give it a another return. So after it call, this is the call to read. And then after read finishes, we're just going to return into that buffer we just read into. And then here I just padded it out to make sure that everything works the same way. And that's it. We send this shellcode. This shellcode is from Shellstorm. It's just a simple execve bin sh. I tried to get the pwn tools shellcraft to work, but my environment wasn't quite configured right. There's some chat in the ASIS CTF IRC if you want to take a look at it. Basically, you have to set the context properly to get the shellcraft stuff to work. And then if you do, so let's do that real quick. So Python from pwn import star, import star. So if I do shellcraft.amd64-sh, this gives me, so this is some assembly that will do a execve bin sh. I think it's exec, yeah, and using the syscall for it. So if I do ASM shellcraft amd64.sh, I get a crash because of it. I have to do context arch is equal to AMD64, OS is equal to Linux. Now it works. So basically what's happening here, at least my understanding of what's happening here, is that it takes the shellcode, which is this thing, it's passing it to AS on the system, which is the assembler with like the new assembler, GNU assembler, However, by default, that is not x86 64. It's either x86 32 or 16-bit. I don't actually know which one. And the shellcode we're giving it is clearly not proper shellcode, or it's not a proper assembly for whatever architecture it is, and it's bailing out and causing errors and things like that. So if you set up the context properly, it works fine. If you don't set up the context, it fails. So I had to go and grab some shellcode off the internet. They're roughly equivalent. They're just slightly different opcodes. So that's start. Let's take a look at start harder. So for start harder, I believe I called that just harder. Very similar, except tools, checksec, file, start hard. NX is turned on. One thing that I did here that I'm not sure I needed to do, but as you can see, this is quite a bit more complicated. As you see, I'm actually running this in a loop. Let's actually run this real quick. Because of ASLR. Because not only is NX turned on, I want tools, checksec, file, start. So not only is NX turned on, but ASLR is also on, which means that I can't just jump back into something. So if I run this, harder, Python exploit, we run this, we're gonna try it once. The first time, look at that. Try this again. Oh no, the reason it's wrapped in a loop here is because their server was acting slowly. I think, maybe. I'm not sure here. But it's the exact same binary, give or take. So for start, it was just a read of 400 hex bytes. For start harder, it is a read of 400 hex bytes onto the stack. Same basic idea, pretty much the same thing, but the actual exploit for it is a fair bit more complicated. So we are calling the same pop RSI R15 gadget. We're loading it with a, not a BSS address, but a, actually, what is that address? Oh. GDB start the, let's just run it. x/20x OX601018. This looks like a BSS address, doesn't it? No, maybe? 601018. This is indeed, so this is the GOT. It's the read GOT. So we are going to read into the GOT some number of bytes. We call that read. We give it the GOT. We just fill R15 with junk. We then call read. And then 405, what is that? x/I OX405C3. We're doing a pop RDI return. So we're loading RDI, so the first argument to that. Oh, right. So we are calling read, but instead of, I'm sorry, I'm a little turned around here. So we called read into the GOT. So we're going to overwrite bytes in the GOT. Then we're going to load RDI with, so basically we're going to execute these bytes. And then after we've executed those, we're going to read into the GOT. And the stuff we're going to put into the GOT, the first time, we're just going to put D0. Basically what that's going to do is that's going to take this address, which if we, other side, take this address, which is currently read. If we read a single byte into that and change the low order byte there to D0, it's now suddenly read. So the first time through, we change read to write. We then pop RDI 1. So now we're going to write, instead of reading from standard in, we're going to write to standard out. We call it again. And what that does is then that's going to print out the same GOT addresses to us. In this case, it's going to dump out 400 hex bytes out of the GOT, but we don't care as long as it doesn't segfault. Did that. We call that write. Now, we're going to get a little bit more complicated. So this is a pop RBP ret gadget. And what we're popping here is we're popping before the write. We then set up RSI and R15. And then we're going to call basically the same gadget again. If we go to where this is, we're actually going to come in right here. So we're going to do this move RSI into RBP minus 20. And then we're going to load up everything and call read again. Basically what we're doing here is, this is a probably way more complicated than it needed to be way of changing read back into read. So we call read, which remaps read into write. We then call write to print out what the addresses in the GOT currently are, which are pointing into libc. Then we do a couple ROP gadgets to set up some arguments. Then we call this again, and this time we're reading after resetting read to read. I know it's confusing. And after that, we're basically just going to set up a few more gadgets. We are doing, so this is the same pop RSI. We're setting up in the GOT again. That's it. Basically, what we've done here is when we do this second read, the address that's going to read into is this address here. I think it's actually just after it or just before it, something like that. So the first time we read, we put in 1 byte, which is D0. We then receive, we read, we get the address for write out of that. We then use the Pwn Tools elf stuff to actually parse all that out. We set up binsh, and basically we just set everything up, and we're just going to call binsh when we're done. Fairly simple. We can run through this real quick. What's the best way to do this? So we are going to, just prior to pushing this, we're going to do a raw input. What this is going to do is this is going to make Python wait on us. So we want to do sudo gdb start password. Did I type out my password? I type out my password. Okay. So we now run this. So the process has started. We want to find our process. Hard. We're going to attach to it 78985. We're currently in this read, so we're going to fin. So we've just finished the read, and we've set up our first buffer. There's no alarm here, so we should be fine stepping through this. So let's do a disp/i rip. Go away. Disassembly flavor Intel. So step, we now have our leave and our return. So if we dump out all these addresses, so we have this first gadget, which is going to load up RDI with these two addresses, and then we're going to call read again. So let's step through that real quick. So pop RSI, pop R15, return. So now RSI is going to be this 601018, and R15 we don't care about. We just put some capital C's in that. We return again, and this time we're going to return into that call to read. So this is using the PLT, GOT. We're now in read. I'm just going to fin here. Fin is the GDB command to finish the run until you would return from the current frame. So regardless of how far this goes down in libc or wherever, it's going to return control to me after this call returns. Let's run through. We're now at the next gadget. Sorry. So if we dump out our stack again. So we just got back here. We're calling. Actually, you know what? I can pull up the script here. So we're now right here. We're going to pop RDI, which is this one. We're going to return again. So, step. And we're going to return. This time we're returning into the same OX 400 gadget, which is read PLT, except because we remapped it using this first call to read, it is now write. Now we write in, we're writing to standard out with the read dot entry. We're going to finish this. And that just printed out to the script what the current entries in the GOT are. We're going to use that to break the ASLR for libc. We're now after that. We're doing this pop RBP. And this is some math to figure out what we need to pop such that when we write a quad word, we will only touch the low byte on it. Basically, we're changing it from D0 back to 70. So let's step. We're popping to set up RSI again. So that RSI is pointing at, RSI is the value we want. We're going to step again. Sorry. Jeez. And then this is that gadget. So we set RBP to be 601018 plus 20 hex minus 7. Basically, that's so that we only mess with the 1 byte at that address plus some junk before it when we use this gadget. So if we dump this right now, or let's just do 2 OX 601018. So this is currently pointing to write. This is the GOT entry for read, which is currently pointing at write. After we execute this instruction, because that is RBP is 601031, so after that executes, we will have remapped write back to read. So if we step, we can see we've now remapped that back to read. And if we check a byte before, look, we trashed. I actually don't know what is immediately prior to this. If we go into, where did you go? Here did you go? Yeah, I don't actually know what this value before it was. It doesn't matter. It's trashed. It's A's now. But we're going to keep stepping. We set up the arguments to read again. These are the default arguments this time, though. However, the default arguments are based off RBP, so they're still pointing into the GOT. We call read. This time it's real read again. We return back, and we are now doing... So we returned back from this. Where are we? So we called here. We called read. We reset read. We return back into... Oh, we return back to the end of the function. So now we set all this up. Oh no, oh no. Oops, I have completely broken everything, haven't I? So if you hit enter in GDB without... If you hit enter in GDB with no commands, it repeats the previous command. The previous command, though, was fin, not SI, like I was used to it being. So instead of stepping one instruction, it returned. So unfortunately, we lost this last little bit, but it should be pretty straightforward, right? So we called read again into the GOT. We sent a whole bunch of bytes to the GOT, and then we're going to call again the read just to get us out. And we get a shell, and that's about that. So those are the two start ones. They're pretty basic. Can you do ROP chains? And if you can do a ROP chain, how do they work? So those were those two. They were pretty straightforward. The other two that I solved during the competition were CRC and Fulang. Trying to think of which of these to do first. I guess let's take a look at CRC first, because I think that's the one that I looked at first during the competition. So CRC, let's open it up real quick in the Binary Ninjas. So CRC was again a binary. That's a pwnable. Who would have thunk it? Again, relatively straightforward. Let's run it real quick, actually. If we run this, basically you get to calculate a CRC, you send it some length of data. I send it some data, 1 byte. I send it 1 byte. Calculates the CRC for me. If we go into this, it's relatively straightforward. The catch here, they welcome to CRC, and it calls get user input number. Okay. The catch here is that calls getS. And it calls getS onto the stack. Okay. So if we do for our choice, stack smashing disconnected, we just completely wrecked whatever's on the stack. So if we take a look at what this binary is doing, it's again, super simple buffer overflow onto the stack, basically the same as the other two, except we now have tools, checksec, file, crcv. Now we have both full railrow and stack canaries and NX turned on, plus some of the fortify sorts of stuff. So basically what that means is a lot of the usual techniques aren't going to work quite as well. So basically what we need to do is we need to find a leak for our cookie. If we can leak out what that cookie is, we're good. We should be able to get everything. And so the way that I ended up solving this is I use the calc CRC function here, which is, again, we're calling getS onto the stack. And we're going to call it with this var 8c, such that the argument to call CRC, which is the address that we're going to calculate the CRC for, we can overwrite this address. So basically the way that our exploit works is, and this is a little complicated, one thing to note here is that I had to comment some of this stuff out because the game server was acting very, very slowly. I think there was some speculation in the IRC that people were just trying to brute force the cookie, which don't do that. It's still a 32-bit system, but that's still greater than, so it's still 24 bits of randomness, which is a little bit much to try and brute force. Like all you're doing is you're hitting the server and hurting everybody. Would not recommend trying that unless you were absolutely sure there is nothing else. So with that in mind, let's just run through this. The first thing I have here is a leak function. And what this function is doing is it is set up to leak out 1 byte at a time of any address. And the way that I do this is, let's come over here. So if we do CRC me, we send it a 1. We're going to calculate a CRC. We're going to calculate 1 byte. We then send 100 A's. Python print A times OX64 plus B times, what's the best way to do this? You know what? Let's just do it this way. We're going to comment this out. We're going to work locally. And we're just going to do leak. We're going to pack or QQQQ. Super simple. So what this is going to do is this is going to immediately segfault. We have a core file. Oh, let's remove that core file. Run it again. Oh, I'm sorry. U32. We need to give it a function accepts an address as a integer, not a string. So we now have a core file, gdb crcme 4. And as you can see, basically ESI is that 515151, which is QQQQ. And we're basically reading a byte out of whatever address we gave it because we overwrote the address to calculate a CRC from. So what I'm doing here is probably not the easiest, well, it was the fastest way for me because I didn't really care, was I wrote this gen CRC function. And all this is doing, and it's dead simple, I didn't feel like reversing out exactly how that CRC algorithm worked, and it wasn't the first one I pulled out of the Python library. So I just wrote this really simple function to open the process, run through all 256 possible bytes, calculate what the CRC is of 1 byte, and then dump that out. So that over here, we can load it and use that as our leak. Basically, when we give it address, we overwrite what the CRC address is. We then look up in this pre-calculated CRC lookup table what that CRC corresponds to as a single byte. One thing to note is that if the way I'm calculating this is a little bit wrong because of how null termination works with getS. Basically, the way that my script ends up working is that the lookup for a new line is actually a null byte that was read. Short version is we have this leak function which leaks out a byte at a time. So we leak out size. And what size is if we come in here, where do they do it? Where is it? Oh, did Party Ninja not grab the symbol? Yeah, they didn't grab the symbol for it. In here someplace. So at some point, they save off a stack address into the GOT. I'm not seeing where it is. So we get an input, we get user input, which is our choice. Our choice was 1, so we come over here. We call it again. Oh, here it is, size. So we save off var90 to the GOT. If we notice, this is actually move ESI, really? Yeah. Anyway, it's actually the address on the stack of that. It's not the value, it's the address on the stack. So if we come in here, these 4 bytes are actually going to be a stack address, not a size, it's a stack address. What we do is we leak out what that stack address is. We use that. We then calculate what the cookie address is, which is the address of size minus 34 bytes. So this is actually the next one up in the frame because we want the cookie out of one of the other frames. It doesn't matter really because with standard GCC, the cookie is the same for every function. So if we get it once, it's the same across the entire process. We just need it once and we're good. So we grab one of them off the stack, we leak it out the exact same way, and then we calculate some addresses. Like I mentioned, the server was super slow. When I was running this locally, I actually did all of this inline. Basically, we get the getS address out of, this is the GOT for getS. Then we get the address for set vbuff. And the reason we grab 2 of these is so that we can use, where is it? Tools, libcdb. So we can use this to find what getS and set vbuff, and basically use this to figure out what libc they were using. Because this was the first 32-bit challenge, I didn't actually know what libc they were using. So I used this to grab their libc. It turns out they're using the same libc as I am locally, so it didn't really matter. But we grab their libc, we then use the getS symbol to calculate what the base address is. We then get system, and we basically just set up a ROP chain now. So we need 28 hex A's to get to the cookie. We then put in the cookie, which we leaked out up here. We then put some more bytes to get all the other stuff between the cookie and the first return address. So that's save frame stuff, things like that. We then put our address, which is system, and then I just threw a whole bunch of these on there. I believe that this is the one that I need, but I can never remember exactly which one it is, so I just threw a whole bunch on there, and it works. So if we do this, we should be able to go. Where do we want to go? Delete the leak that will crash us. We go over here. We just run this real quick. Python exploit. Pops us, should pop us a shell. Not gonna pop us a shell? Why do you not pop us a shell? Oh, in any case, it works sometimes. I'm not quite sure why it's failing here. But the short version is that this second ROP chain should pop a shell for us. It should work fine. So that was CRC. Basically, the idea that it's another really simple buffer overflow. The catch being you have to use the CRC function to leak out addresses. I believe somebody else mentioned solving it a different way for their leak. Like they still use the CRC, but I don't know how they used the leak for it. I think the basics are pretty much the same, that you get a leak, you then blow away a whole bunch of you leak out the cookie somehow, you blow away a big chunk of the stack, and you just win. So, final challenge that I solved that we're going to run through real quick is foolang. And so foolang was a interesting challenge. So foolang was a basically I don't know if I want to call it an emulator or if I want to call it a interpreter. Because the basic version is that there is the foo interpreter. So it reads in 96 hexabytes. Where do we read things in? So we do an fgetS of 96 hexabytes. We save it off here. We call strlen on it. And then we're going to call foo interpreter. And so foo interpreter is going to get called for each pair of 2 bytes. We make sure that we have not reached the end. If we reach the end, we bail out. And for each of these, we're going to call foo interpreter. And so foo interpreter is going to compare the first byte, to, and I want to display this as a character, is going to be a colon. And then based on I'm using the R hotkey here to switch to a ASCII representation. Based on what that character is, it's going to run some operation. So that's basics of it. And so I'm not quite sure what to call this because it's kind of like an emulator for a processor because it has some memory associated with it. So there's this foo memory region that we use. But it's more like a program interpreter because it's just interpreting a program that we give it. But in any case, let's take a look at what the exploit looked like. So the exploit for this, foolang, exploit.pop. Ooh, did I not? Ooh, I don't know if I pushed this one. Well then, so foolang was pretty simple. So I have the address of foo, which is, it starts at this 804 A080. This is where the data starts. We're then going to read backwards until we get to where foo is. So we come back here. So foo, we can read, we can decrement or increment foo, which is the program counter in that memory. I don't know, or it's the pointer into that memory. We can also use plus and minus. And what that's going to do is, so we read in foo, we then read the byte out of foo, and we either increment or decrement that byte. We also have the ability to put car or get car out of that memory address. So foo starts out pointing at data, and then we can manipulate it from there. So what we do in our exploit here is we walk backwards 20 bytes. So foo, instead of pointing at data, now points at foo. We then read in a single byte. So we read in a byte, and we're going to change the low byte of that address to 28. So we read in a byte, and now foo points at the set vbuff in the GOT. We then use 4 sets of instructions. So colon is put car, and then colon alligator goes that direction, so greater than. I think that's right. So colon is puts a character, and then colon greater than goes to the next byte. So we print out all 4 bytes of the set vbuff address in the GOT. After we've walked through all that, we use colon close paren, and what that's doing is that's giving us a new line. I don't think this is actually necessary. I was just using it to be easy to read stuff out. So we do that. We then walk backwards 4 bytes, and we're now going to write over what that was. Oh, I'm sorry. We read out 8 of these addresses, not 4 of them. We read out both set vbuff and put car. Because we need 2 addresses in order to use the libc database to identify what libc they're using. And as you can see here, this is my local libc. This is the remote libc from the server, which I used the libcdb to find. So we read out the pointers for set vbuff and put car on libc. We then use this paren to print out not implemented, I think. Come on. Yeah, not implemented yet. And we're just using that to identify when we've printed out all the bytes. We then walk back to the start of put car, I guess. We then, the colon dot is going to write a byte. It's going to use get car to write a byte into the current address. We then step ahead every time. And then when we use colon, it's going to call put car again to print out a byte to us, except we have now remapped that to instead be one of the bespoke gadgets in this. And as you'll notice, I actually got to use one of those bespoke gadgets. Didn't I? I think I did. Oh, right. So this address is one of the addresses out of their libc. The comments down here are from my libc. So they're actually a little bit different. Like the comments are different, but this is what the output of one gadget looks like. I know I mentioned this several weeks ago, but one gadget is a script by David. I'm not going to remember his name. We'll pull up our Python, but basically with this, that's not what I wanted. One gadget for libc. So it will print out, here are the addresses that we found in the binary, which are a one-shot gadget, is what they call it. I've also heard them called bespoke gadgets. I think that's what I usually call them, is a bespoke gadget. But the short version is, it's a single gadget that will call execve or execl or something similar of binsh. And because of how libc works, for instructions like system, they have to have a copy of this. The catch is that certain arguments, so for execve, the like argv and argv and environment have to be realistic at least. So for this one, we need ASI to be a read-write area of libc, or I think just a general read-write area. And the address at the stack offset here has to at least look kind of realistic. It either needs to be a null byte or a null pointer, or it needs to point at something that looks like a argv would. And then there's several gadgets like this. We're using one of them here to get what we want, which is just to pop a shell. So those are the challenges that I actually managed to solve during the competition. So if you have any questions, feel free to say something in the chat. I can go back to any of these, but for now, let's take a look at the one that I didn't manage to solve. So this was, and let's actually pop it up before we try and RE it too much. So this is Kanak. So we have Kanak MGF. We have 5 options. We can run away, which just exits the process. We can allocate some memory. We give it some bytes. We can free memory. We can read memory. That's it. There's also pray for Allah. And pray for Allah asks us, where is the Quran? Let's not dump my stuff out on camera. But we give it a file, and it prints out the first 400 hex bytes, I think, of that file. And so the way that I use this is I use this to grab the proc self maps to break ASLR, because proc self maps will be, according to the OS, what pages are currently mapped in for the current process. So proc self says go into the proc directory, proc file system, and I want self, which is my current process. You can see in here there's a whole bunch of different things you can get out. Cat maps. This prints out all of the libraries that are currently loaded. As you can see, there's a ton of them, I guess for screen. But we can also, I guess bash. We can also see, so we have our executable. We have the current process, the current working directory. So if I do c ... and I do ll of self, we can see that the current working directory has changed, so has the executable, because it is using the, so when I do ll of self, it is ls that is opening self. So the executable is ls. But anyway, there's a ton of stuff in here. I think the most useful one is typically maps, which has the maps of the current process. But there's also mem. We're not going to be able to cat this. But mem, if we had access to it, so if we do our cat self mem, what that is that is a file handle into the current process's memory. So you'd have to be able to seek to a valid address in it. But if you did, so I'm in Python. I want to f is equal to open proc self mem. I want w plus, I think is what I want here. No. Oh, I should actually give it a string, shouldn't I? No, type better. So if I do f.seek, I think it'll work. .read 4 bytes. We get the elf header. So I seek to OX 400,000 hex, which is going to be the start of the data section in memory. So we can see here, it's just the stuff. And I can also do elf. I can write here many A's. And what we're actually going to get here, did that actually work? We've actually blown away a big chunk of the binary. So occasionally this comes up where you'll be able to use proc self mem to actually get code execution on a binary where you wouldn't be able to normally. Basically, if instead of doing 200, if I did, that many, I eventually get a core dump because I overwrote the function that I'm currently in. We show details here. We should see, come on. If we go into the roll better, we can see this ferr rex.b is probably a capital A, I think. But yeah, registers. We want registers. So RCX is 414141. R9 is 414141. R10 is 414141. RIP is not, but yeah, we smashed all over a ton of addresses. Everything is broken because we opened up our own memory and we wrote into it, which is kind of to be expected. If we write into the executable's current page, it's going to crash. But this is all kind of superfluous. So we use that pray for Quran in the Kanak MGF. that how it was pronounced? We use that to read out and get our ASLR. So we send 2, we're going to receive until we get the question from us. We then send proc self maps. Right. So I'm asking the chat here, Python crashed. Right. So when Python opens proc self mem here, it is opening its current process memory. So Python is opening its own memory. So when we read from it, we're actually reading the Python memory from this file handle. So it's basically just a handle into your own process, and it also doesn't respect NX. So we can write into areas that are normally non-writable because it's going a roundabout way of accessing it. This isn't typically that useful. The only times I can think of this actually coming up and being useful are maybe once or twice in many years of CTF stuff. But it's something to keep in mind. I have used it a couple times for hackier things. I think the only time I've seen it used in a CTF was for a Python jail, where for whatever reason you were able to use that to get code execution. You were able to open your own process memory and write bytes into it and use that to get code execution. Doesn't come up very often though. So back to the binary. We use this to dump out proc self maps, and basically we take our maps, we split it up, we get the heap one, and we get the address for libc. So now we know both where our heap is and where libc is. And then we've got a couple functions here to allocate a new buffer and to free a new buffer. That's it. One thing to note, if we open this up, is there is additionally an off by 1. So if we open this up, so there's the main bug, which is basically that we come in here, we read, oh, did you not identify these? That's unfortunate. So how does this work? So we did racks times 8 plus this address, where racks is the index. So this should be a jump table. That does not look, oh yeah, that looks like a jump table, doesn't it? Quad word there. We have a jump table here. I want, well, let's just do this manually. Quad word. There's a hotkey to do this more efficiently, but I don't remember what it is. So these are our options. If we come in here, make this a function. This is calling exit. We're just identifying these functions real quick. So we now have several new functions here. And so this function, what are we doing here? We will call read. We call this function, which gives us our menu. So if we send it 0, it just loops back around to itself. Calls read, stir to L. If it is below 5, we come in here and we hit our jump table. Okay. This is 0. This one, we set EAX0 and we call this function. This function, we print out the length that we want. It uses scanf to get that length. It then mallocs that many bytes, and then it reads in that many bytes into the malloc buffer. So to start with, there's a little bit of bug here in that if we give it something that malloc won't return, we could get a write to null, but that's not going to be super useful. So this is do alloc. This is going to be the pray for Allah. So do pray. We can see here, where's crayon? We call printf, we call scanf with a ton of bytes. We then fopen that file, we fread it. One thing to note is that if we give it a file which is not valid for fopen, this fread is going to cause a seg fault. So we have to give it a valid file, which doesn't matter if we're giving it proc self maps because that's always going to be a valid file. But one thing that is important is that this address right here. And can I name this? Oh, I can name this. File name. So we have that. Our third option is, I believe, the do free. Yep, do free. And let's just name this last one real quick. So this is going to be the do read. And so if we take a look at these two functions, do read and do free, as you notice, they're basically identical. The only difference between these two functions is that free calls free, read calls read. And what they're acting on, so it asks for the number, which is an index. So it gets calls printf, calls scanf. It's called scanf. And it is going to save, so sorry, I'm blanking here for a second here. So it's calling scanf with %u, and it's going to save it into var14. It saves that off here. Make sure that it's less than 64 hex, which is 100 decimal. And if it is less than that, it's going to use it. Or it's going to use it as an index into this. One thing to note we want to give it 100. So we have all of these here. Is that if we remember, this right here is the file name that we supplied it. And if we take a look at what this is, the comparison is going to be a jump below or equal. So we can actually send it 100 as the file name. So let's do that real quick. What was this called? This was Kanak. I used a capital C for some reason. So we're going to pray for it. We're going to run it. I want to pray. I'm going to give it sub A's here. Proc self maps. We did that. I now want to read, and we're going to read from entry at 100. And if we take a look at this, the entry we are reading from, set disassembly flavor intel, we are reading from racks, and that's actually 00400. So it's actually reading this right here. The contents of the file we just read are what caused the seg fault here. Basically what's happening is the area that it's using there. So we do proc self maps. We then use it again, 1, 2, 3, 4. We have some A's here. We now want to read from 100. We can actually control the region we read from. We can use this to read arbitrary memory if we want to. However, because we already have the ASR defeated, I'm not sure this is entirely useful. But it is something to note that this is a second bug in this binary that I'm not sure was entirely intended. So those are do free and do read. The important part here, and the root of the bug that we're going to take advantage of, let me close some of these real quick, is that, sure, we don't care. Do free does not attempt to verify that the buffer we're going to try and free was ever allocated or is currently allocated. So when call do alloc, it takes it mallocs some memory, and it's going to save it off into that into this array of list of pointers, so we can read from it or write to it, or read from it or free it. Makes sense. So that's relatively straightforward. It's a pretty standard heap exploitation challenge. The primitives we have here, and let's actually take a moment to talk about what I mean by when I say primitives here. For most vulnerabilities, you can break it down into some set of primitives. What is this set of things that I can do with the binary that are somehow useful for exploitation? So in this case, the primitives I have are I can allocate I can call malloc with an argument of my choice. I can write up to that many bytes into the allocated buffer. I can then read any allocated buffer, or I can read any address. I can free any of my currently allocated buffers, and I can free an arbitrary address. Sounds pretty straightforward. Like, it seems like a fairly standard heap exploitation challenge. So why did I spend so long on it? And the answer is, the reason I spent so long on it is because I overthought things a little bit too much. So if we go and we reference the how to heap stuff, so again, I know I've mentioned this several times. This is from Shellfish. It's on their GitHub. It is amazing for learning or referencing how to do heap exploitation stuff with glibc and dlmalloc. They have very good examples of what to do for each of these and some CTF challenges where they did it. So the first thing is, since we can make it an arbitrary size that we're doing, the fast bin stuff is the easiest way to do that. So the fast bin dupe into stack stuff is basically what we're going to do, what we would want to do here, which is you free something to get into the fast bin. So to be in the fast bin, it has to be under a certain size. I believe by default on most systems, it is 80 hex bytes. So we free a buffer, which is malloced with 8, so way under that. And actually, here, let us do this real quick. So I have these, I've actually cloned this locally because I find it super useful to be able to come in here sometimes. I want the fast bin dupe into stack and just run it. So we called malloc 3 times here. Each time, you notice it goes up 20 hex bytes for each of these because there's the metadata in front of it. We free the first one. If you free it again, it will crash because it is at the top of the free list. So we free the next one. We can't free it. Now we can free it again because it's not the head of the list. So basically what they've done here is they've freed it multiple times. So now we have first one, second one, first one again. They call malloc twice. So now they have the first one, they have a pointer to it. They can write to it. They have a pointer to the second one. But the first one is still in the free list. So they write some bytes into it. But the important part here is that when they try and unlink this, unlink is a very loose term. In order for malloc to return something out of the fast bin list, the fake free size needs to be correct. Basically what that means is that malloc, well, let's pull up the source code for it. Whoa, a Bach malloc. I think I pulled this up on the stream before. This is just a online viewer for source code. It's already been populated with glibc stuff, and I've used this quite a bit for some of the heap exploitation stuff. So if we go into, let's start in malloc. So int, only one underscore, int malloc. We want to go to where it's actually called. So we have int malloc. We check the request. Oh, no, I don't want that. If it is less than get max fast. So if it fits in the fast bin, we're going to get the index into fast bins. We're going to get a pointer to that. We are then going to take the, so PP is the victim, what they call it. And basically, we're going to try and yank that out. If it's non-zero, so basically, we want to get the first value out of that free list for the fast bin that is not the fast bin itself. So if there's some kind of like circular thing, or we've somehow pointed the fast bin, at the bin itself, it won't return that. If it's not zero, then there's something in there. We then check to make sure that the chunk size of whatever is in that fast bin is equal to the index. So what exactly does that mean? Well, the short version is that the byte or the quad word immediately prior to what we're trying to get needs to be the same as the index for the bin we're getting, which is going to be the size of what we allocate. And that's the root of the problem here. And the reason why I spent so very, very long on this. As you may remember, on a stream not too long ago, I believe it was 2 or 3 weeks ago, we talked about exactly this, which is that when you do fast bin exploitation, you have to have that size properly set up. If you don't, it will return something wrong. The catch is that that does not check that the memory addresses you are using are aligned at all. So the size can be, reload this up real quick. No. Oh, that's why. Yes. Reload this up. Run it. Where is our got? So if we come in here, 602078, OX602078, we can actually use this 40 right here. Well, not this one, but we could use a 40 if we come up a little higher. So, and a little bit higher. Is that not? Oh, did I put too many? Yeah. So if we go through here, we can use one of these. In particular, we can use this 60 right here. So 602000 is the stuff right here for, I can never remember what these first couple things are before the GOT, but we can use this 600 as the size. So we want OX602000 minus 2. So if we do this, x/x, oh, I'm sorry, plus 2? Plus 2. Now, math is hard. Plus 2 minus 8. How? 602 minus 2. That, what? Plus 2? How do computers work? Minus 7? Okay, let's do this the other way. So we have this. We want 20bx. So we want single bytes. So which of these will work? Right now, none of them. But so we need this. How are we going to do this? So we need the low byte to be something that looks like a valid size. Because if it is, it's going to let us return that as a pointer. And so I should note, at this point, I am doing this relatively blind. I am at least somewhat familiar with what I'm trying to do, in that I've done it in previous challenges. But for this particular challenge, I have not actually landed this. So let's think about what we can do here. So we need to have something that's going to look like a valid size. And if it does, it will let us return this. So I would think, how does the math here work? What we want to do here is we want to get it such that we can use part of this pointer as the size. What is this? How does this size actually work? If we go back over to this, and I say fastbin index chunk size, index is a regular int. fastbin index returns an unsigned int. So we'll actually cast that to an int, whatever it is. So we actually only care about the 24 bits, or I'm sorry, 32 bits, not the full 64 bits, right? So if we do this x/x, and I want a wide x, OX 602.002, that is a valid size for a fastbin. So if we point our fastbin at that address, I should be able to get it to return something which is that size, assuming that I understand how any of this works at all. So how do we actually do that? So victim is pointing at, well, let's do this real quick. So what we're going to do here, and again, you'll notice here, I've got tons of code commented out from this because this is the script I was using during the CTF to try and do things. So this is not at all an example of good code. So we come in here, we're going to make two that are of size 60 hex, which I think is, what we want. So we have this, let's close this out. This was Kanak, Python, exploit, yes, sudo bang bang, type in my password, bang ps aux, and this is pray. We want to attach to 802.83. We're now in this. And so if I actually dump out all of this stuff, so 602.0218, so this is the GOT, and down here we see the pointers that could, no, I'm sorry. I spent quite a lot of time looking at this over the weekend, so unfortunately some of these are memorized now. So 602100 is what I want. 602100. And so we see here, this is the list of addresses that we could free. And like I thought, if we notice, those are 70 hex apart. So they're a little bit farther apart than we actually want them to be. So we actually want 50 hex because of the size of the metadata. And so we go through, we set up both of these. We now want to free 0, free 0, free 1. Oh no. And we're actually going to set up another one after this. This is going to be our C1. We're going to make it a lot bigger. And the reason for this is we want to make sure that our buffer that we get back is not consolidated. We want to make sure it stays in the fastbin for us. So we've done this. We'll save it, restart it. We want to find what it is. Attach to 80319. Yes. We dump all of this out. So we now see we have these. They should both be freed. So if we actually dump out what is in them. So we have the first one. And let's search. Oh, yeah. So this is what our free list currently looks like. So we have, actually, let's dump that out too. And main arena. So we actually have, here's the bucket for our free list. The first entry in our free list is 1B56060. That's pointing right here. If we look at what that actually contains, so we have this, we have a size, we have the next entry in the fast bins, and then we have junk from, I guess what I sent it? I don't know. Oh, so this is the back pointer that was populated for some reason. I'm not sure it actually should have been populated. Yeah, I'm not sure where some of these pointers came from. But the important thing is because this is in the fast bin, this is the pointer to the next element in the fast bin, which is up here, and it has the same size. So when we go and call malloc, what it's going to do is it's going to, if we malloc 60 hex bytes right now, or 50 hex bytes right now. It's going to look in the fast bin. It's going to say, oh, look, I have a fast bin for that size. Here's the first element in it. It's going to then go to 1B56060. It's going to say, oh, what size are you? Oh, 60, because it's going to chop off the bottom 3 bits because those are flags for different things. It's going to say, oh, you're 60 hex, which is the size we expected you to be. So we can return you as a pointer. And then it's going to take this pointer and it's going to put it into the fast bin as the next thing to use. So we actually come in here and do this. Kills it because, let's get rid of that real quick. So we call alarm. Where do we call alarm? We call alarm here. So we call alarm here. And I want to patch convert to NOP. So instead of calling alarm, we're going to do nothing. Save file contents. Yes. Yes, replace it. So what we did here is we just used Binary Ninja to get rid of that alarm, which is how the alarm is how they do the timer for that timeout. And we just said, you know what, we'd rather you didn't do that timeout. We'd rather do this on our own. So we want to attach to this, which this is going to let us mess around in GDB a lot more and not have problems. 6021, and we have something similar. You will notice that it's different pointers because of ASLR. So now what are we doing? We want to make an allocation. The length is 50 hex, which is 80 bytes, right? That sounds right, right? 5 times 16, 800 bytes? 800 bytes sounds much better. Let's just ask the internet. Is the main arena symbol present in all binaries that are not stripped? Maybe. So somebody in the chat was just asking, is the main arena symbol present in all binaries that aren't stripped? I believe it's present in most, but there are conditions where it isn't. And unfortunately, I don't have a good explanation for why that is. Certain libcs have it and certain libcs don't. It comes down to not the binary, but the libc that you're using. And I found that libcs that are relatively close to whatever system I'm running GDB from, GDB is able to find that symbol for most of the time. So if I'm running it locally and I'm not importing a new GDB or a new libc, so if I'm not doing like LD preload a new libc, GDB can usually find the symbol. However, it can't always. On my system, it always finds it. Sometimes when I import a different libc, it can find it. But it's based on the libc, not the binary, is the short answer. And my understanding is that it probably has to do with using the same setup as the GDB was compiled with, but I don't know that for sure. So that's that. We want 80 bytes. So going back to what we were doing before, we're going to make an allocation of 80 bytes. We're going to send it some bytes. Okay, so now if we break in here, we will see that the pointer that was returned from malloc is DCA070, which is the same as the second pointer that was returned from malloc. And if we go in here and we do, we dump from the main arena again, we see that that bin has changed to now point at this buffer. So the short version here is it works. We freed that, and it's returning things out of the free bin. And if we wanted to, we can come in here, we can do, I want to free one again. And look, we get a double free assert because it is able to tell that we have freed the same pointer twice. Basically, the way that it knows this is it actually checks to see what the next pointer is. So those flags in that size, one of them is if the previous pointer is, or the previous chunk is currently allocated. And when we freed it the first time, it set that flag to 0. When we freed it a second time, free says, wait a minute, that's not what you're supposed to be able to do. You can't free the same pointer twice without allocating it in between. So that's what that is. Hopefully this won't be too loud. I was getting a little bit of static. Can you hear me okay? Hopefully you can hear me okay. But my headphones that I can kind of hear myself on, I was getting a wee bit of static there. So hopefully all the sound is good. But going into what we're doing here. So what we should be doing here, and what should work, is we should be able to give it a pointer into the GOT that is misaligned for this size, such that we're able to take advantage of that. And there's several things that we're going to need to do to make this actually work. So the first thing is we're going to need to allocate some buffers and free them. So we're going to allocate 2 buffers that are 50 hex bytes. We're gonna allocate 3 buffers that are 50 hex bytes. And I'm going to see, is this gonna work? Do I have GIMP installed here? I do have GIMP. Do I actually want to try and do this in GIMP? Yeah, we're gonna be risky here. I'm gonna see if I can do some drawing in GIMP. So we're gonna have chunk 1, chunk 2, and chunk 3. This is, as you'll note, if I was doing this on Twitch, I would currently classify this as a creative stream, because I'm showing you all how to do awful, awful things with GIMP that make no sense at all, but hopefully make things look a little bit better. But I want a... What is it I'm looking for? I want the tools. I want brushes? No, I don't want brushes. I want to be able to write some text. It's not... Anyway, so this is going to be 50, this is going to be 50, and this is going to be 50. And what that's going to do is that's going to let us free all 3 of these. We're going to allocate 1 big buffer underneath it all. And this buffer, we're going to be able to write whatever we want into it. And the important thing is that we're going to write into this buffer as if this second block was, or the second chunk was freed, but the freed pointer points into the GOT instead. Let me think about this for a second. Do we need this third block? So the reason I'm thinking we need this third block is so that it thinks that this chunk is still free. But because when we allocate this block, it's going to set, so when we allocate a block here, if we only did these 2, if we allocate a block here, it's going to set the in-use bit right here to be 1, which means that this block, if we got it to return, would also be free, or would also be allocated. We take a look at it. We check to make sure that it's the right size. We don't verify that it isn't in use. So that might work. Let's go to try and see. So going back to our picture here, the short, awful graphics here are basically, we're going to allocate 2 buffers. We're then going to free both of them such that this block is the top of the fast bin. We're then going to cause up here an allocation that is large enough to cause a consolidation. And the reason we're doing that is we need malloc to return these 2, we want it to return these 2 bins as the first entry for us. So we can put some bytes into it. So let's get that set up real quick. So we come in here. Where's my script? Here's my script. So we allocated 2 buffers. We freed both of them such that B is at the top of the fast bin list. Although I don't... Does it matter if it is or not? So unfortunately, let's think about this a little bit more. So the problem here, and what's going to be difficult, is that, yeah, we're going to make 3 of these. And I will explain why in just a second. So we have C and we have D. So we freed all of these. We then want to alloc A times 8. And the size we want is 50 hex for the first one, plus 60 hex times 2 for the second two. So we want one buffer, which is that entire size. And we're going to actually change the message we put into it to be a buff. We're going to have to build up this buff. So the reason we're doing this is what we're going to do is we're going to allocate. So we're going to allocate all 3 of these bins. We're then going to how do I use GIMP? Where did all my stuff go? All I want is paint. Like, here we go. Colors. Colors. I want to paint with white. Yep. Of course, you're not just going to erase for me. Can I? Wow, this is. Yeah, we're just going to close this. Discard changes. We're going to create a new thing. And we're going to go back to black. So, 3 bins that are each 50 hex in size. We then free all of them. We're then going to cause a consolidation up here. And then we're going to allocate a single buffer, which is this size. So we do this. I believe anything over 400 hex will by default cause a consolidation. Note that the 500 hex does not fit inside those 3 empty bins. So what we should see is that all 3 of these are ready to be returned. And then when we make this next allocation of buff, we should see, let's just put some cues in here so we can identify. When we do this, what we should see is that the start of the heap has cues in it and should be of length such that it fits that entire area. So we save this. Let's kill that. We're going to come over here, do ps ux grep a. We're going to attach to 80527. So we've attached to this thing. Okay, well, we have attached to this thing. So let's take a look at what this looks like. 602. We actually take a look at this. So what we notice, we have the first pointer, and then we have 60 hex later, 60 hex later, and then we have 2 values which should be both 500 hex in size. And then the final pointer is back where this first one is. So if we take a look at this, x/20gx, we can see that right at the top of the heap, we have all those cues. And one thing that's important here is that we have here these allocations. It should be noted, though, that because of how the consolidation works, it's actually changed the metadata here because it consolidated the second 2 together, and then it consolidated the first one with the second 2. So we had 6-1, and then there would have been a pointer here. When we triggered the consolidation, we consolidated these 2 together, so they're now C1 in size, and then it tried to consolidate backwards again, and it combined all these together, so that when we made that allocation, it returned this entire chunk of memory. Rather than just a little chunk, it returns a big chunk for us. Awesome. We can actually see right here where it, once it had consolidated all of this, it wrote in what the size of all that was. Because once we went over the threshold for being a fast bin, part of the metadata for a freed regular bin is at the end of the chunk, the size of that chunk is. And that's so that you can go backwards and forwards more easily for larger chunks. So what we're going to do here is we're going to change buff. Instead of being just a few cues, we're going to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 quad words worth of junk. So we want buff is equal to q times 8 times 11. So we want 11 quad words of that. So that should fill all the way up to here. We then want to write in a size, which is going to be buff plus equals, we're going to pack 60. What size do we want here? We want 61, I think. And the reason we want 61 as opposed to 60 is because the 1 says that the previous chunk is in use. So this stuff right here is in use. And then we want a chunk of size 60 in here. So we write, that's the size we want. We don't care about the rest of the data. So we're going to write buff plus equals A's. And we want 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 quad words worth of that. And then we need to write another size there. And we're just going to do the exact same thing again. And so what this is doing is this is setting up a fake chunk in that region. So this is going to set it up so that we can pass this 11D6070 to free again and add it into the fast bin. Should just work. And the reason we're going to do this is we're going to set all this up. We're going to free that. We're going to free one. So let's actually, yeah. Let's pause here so we can actually inspect it. Then we're going to do free one. And free one is going to free the 50 hex bytes that we just set up a fake chunk at. Then we're going to free 0. And what that's going to do is that's going to free the entire chunk now. So this entire 120 hex byte chunk, that's going to get freed. And the reason we're doing that, both of that, is the only way that we can write into a chunk is when we make the allocation. So if in order for us to overwrite this chunk, we need to free it again. So we free it. We then are going to, so we freed 1, we freed 0. Now that I think about it, let's free 0 and then 1. I don't know if this matters. We'll see if it does or not. Let's go ahead and run this real quick. So we're going to break out of here. We then run it again. Bang PSAUX grep ray. Okay, so 80571. We are now in the first of these. So 602 OX 602100. So where did we break in? So we broke in here. So what we should see is if we dump here, other side, x/20gx, that. We see here are our queues, and then starting at 70, we can see our fake chunk is set up. So we have our fake size of 61, which is the old real size, followed by some bytes, followed by the size of the next chunk. And all that looks like it lines up just fine. And basically what that does is when we go to free 1 here, that's going to add this chunk to the fast bin list as being free. And then we need to free both of these. So if we come back over here, we continue, break in again. Let's take a look at what that actually looks like. So if we take a look at it, we now have this chunk has the forward and back links because it's in the regular bin size. We've now freed this object. We can see here that it's because it's in the fast bin size, it wrote null bytes there to denote that there's nothing there. And if we come in here, we should see at main arena, we should see that indeed DB7060, which is this unit right here, is in the fast bin. And where would it be? This is in, I think it's in the unsorted bin right now because we haven't triggered a sorting event yet. Is this big chunk. So if we come back over here again, we now want to alloc buff again of the same size. So let's just yank that. Oh no, I vimmed poorly there. Except this time, we're going to have basically the same buff, except, oops, we have to change a few things. So instead of being a whole bunch of A's, we want 10 sets of A's, and we want the next pointer. So if you remember what we had said before, the pointer needs to be something that the size looks good on. So 602, 601, 018. So this isn't the GOT. That does not look like the GOT to me. What have I done? I apparently don't remember what my GOT addresses are. This is the real downside to looking at a whole bunch of challenges in the same weekend, especially like messing with GDB a ton, is that I think I remember some of these addresses when I really don't remember them at all. So what we said here is that if we gave it this address, if we gave it 602.002, it should look at that and say, yes, that looks like a proper size for a chunk. So 602.002. If we put that pointer in, I think it should let us allocate that GOT entry for us. And then as a final thing, is we're going to take this right here. We're going to put it in here. We're going to put, yeah. Oh no, I don't want to, no, I don't want this at all. What have you done? What have you done? So in the chat, somebody recommended installing PETA. I actually don't like using PETA. So GDB PETA is, I don't remember what it stands for, but it's, the P stands for something, and then it's exploit development something. It's basically a whole bunch of extensions for GDB in order to make it better for doing exploitation. And I know a lot of people like using it because there's a whole bunch of features like the telescoping stuff. They have some heap analysis stuff built into it. There's a ton of useful features. However, I actually find that with the workflow that I usually use for exploitation, I don't actually like having all that information. I find it kind of distracting. It also adds a whole bunch of colors that, again, I find a little bit distracting. And for the most part, it is at most one extra command away if I decide I want that information. So personally, I don't like using the GDB PETA stuff. I like using just the bare GDB. As you might have noticed, I actually tend to use a lot of bare tools. I use Vim with no extensions. I like using GDB with no extensions, just because that's the way that I find I work best. Part of that is that I like to blow away my machines on a fairly regular basis. And if it takes a long time to set them back up, I find it kind of distracting and annoying. But the short version is, GDB PETA is actually a really great tool if you like having it. It's very worth trying. Personally, I don't like using it though. So to each their own, right? So where were we? So we're going to run this again. And if all this works the way that I think it should work, when we make this second buff, we're going to overwrite the freed chunk, which is in the fast bin, such that it thinks the next chunk is going to be valid. So again, assuming all this works the way that I really hope it works now that I'm doing it live. Yes, I am cyber Amish. Thank you. I think it is very much a kind of get off my lawn type of comment. I got used to using GDB before GDB PETA was popular or possible around at all. Like I started doing some of the CTF stuff 7 years ago now, I think. At that point, GDB by itself was plenty. So before GDB PETA, and I got used to using it, and my fingers type things, and GDB PETA has other things I should be typing instead of the things that are in my head right now in muscle memory. It's the same reason that, like, if you talk to people who've been doing exploitation for a long time, They use a lot of old tools because it's what they learned how to use and what they were efficient with, and it isn't worth their time to learn how to use something new, even if it would be a little bit faster. Like, it's the same reason people use Vim or Emacs, even though there might be something faster. I know I could start a huge flame war over that one, but there's a lot of really good features in some of the like modern IDEs. But when I do development, I still use Vim because Vim is what I know, and even if, Visual Studio might let me, so let's say Visual Studio, if I knew how to use Visual Studio as well as I knew how to use Vim, was 10% faster, the time to learn it is such that it isn't worth the time to learn it. Like, I'd have to do tons of work with it to get anywhere. But this is all a big tangent. Let's go land this exploit. So just back on track here. What we have here is we sent some buffers in here. 20GX OX602100. So we sent in our first set of buffers. And what we have here, we have now overwritten. Have we overwritten the first one? So our first raw input, we have now overwritten the freed chunk so that we can now free it twice. We continue, break in again, and we see we now have basically what we would expect to see here. This is actually what we had previously. We had, this is just before we overwrite this again. So if everything works the way that hopefully it works, when we run again, we did not successfully do this. That is unfortunate. Damn. Okay. So, let's see what's happening here. So we are now here. We want to make an allocation, 80 bytes in length. And it is saying memory corruption fast. Oh, right. Duh. So it's complaining about the address we're giving it. And the reason it's complaining, hopefully, is because the pointer that we should have put in here is the, what do they call it? It's the internal pointer, not the pointer that was returned to malloc. So I gave it the pointer, I gave it the pointer to what I want it to think the size is. So I actually want to give it 8 bytes prior to that, so that it thinks that that's the start of the metadata. Let's try this again. Run through, we load the binary, we continue out, give it 80 bytes. Yeah, look at that. Yeah. Okay. So hopefully all this works now. And that segfault down there should be like it's calling printf or something out of the GOT, and we've trashed the GOT. So 80722, continue. What? No, that's not how that's supposed to work. What? No. 602021. Yeah, no, it totally returned the GOT there. Oh, I didn't trash enough the GOT. That's my problem. OX50. Actually, let's do this the right way. I want to do cyclic OX50. So cyclic, if you're not familiar with it, that's one of the Pwn tools things, and that creates a, I'm going to look it up after this. It's a cycle of characters that will be globally unique. So I do Python exploit here. I want to do ps aux grep pray. We're going to attach again here. Going to continue. Enter, enter, enter. Oh, look, a zigzag v in puts. Okay. So when it went to go call puts, it caused a zigzag v. And if we do rip, I really need to get this set up properly. So it tried to execute what is, or try to jump to what is at this address. What is at this address is junk. So let's go back and talk through what we're doing here. So we now have control of PC. And to walk through real quick, since we're getting a little close on time here, what happened. So we allocated these 3 buffers. We then freed all 3 of these buffers. And then we allocated 1 big buffer underneath them. We also allocated a big buffer up here in order to consolidate all these and make sure we allocated 2 big buffers up there in order to make sure that these all got returned properly into the free area so we can allocate this big buffer. We allocate this big buffer. And in here, make this in red, we write in a fake chunk here. And this fake chunk looks exactly like this chunk did previously. And because there's a stale pointer to this in the list of buffers we can free, we're able to come back in and we're able to free this big thing and then free this thing too. And this means that this pointer right here ends up in the fastbin list. And then this is also in the normal bins list. So this is in the fast bins. We then allocate this big buffer again. And this time we're going to again write a fake chunk here. This fake chunk is going to be this is going to have a back pointer into the GOT for us. And it's a misaligned pointer such that we're able to use the top byte of a pointer there and use that as the size. So when we freed this, we're now going to free 2 new buffers of size 50 each. And so this second pointer is actually the second one is going to be in the GOT. Basically, that gets us code execution when it goes to call puts. So let's get this finished real quick. So instead of this being a cyclic, we're going to send buff. Buff is going to be a cyclic OX50, but we want to stop it at cyclic OX50 dot index P64, this thing right here. So this is the address that we are faulting on. So we want to write up until that, and then buff plus equals P64 address. So if all this works the way that it should, which hopefully it works the way that it should, if I do address is equal to U64 Z times 8, we should see this faulting on Z's now when we go to jump to it. And before I forget, someone in the chat asked to show how to use pwn gdb plus breakpoint command to dump memory when a breakpoint is hit. So if you're talking about using the pwn tools GDB stuff, I actually can't use it here. So there is stuff in pwn tools to be able to pop up a GDB session attached to it. However, I'm using Screen, which, because of how all the terminal emulation stuff works, if you use the pwn tools GDB stubs, it tries to pop it up in X for you in a new window with GDB attached. I actually can't use that because of Screen. Screen actually intercepts it and doesn't let me actually get that properly. So I can't use that. So that's why I have to do this like complicated stuff to attach later and stuff like that. But I find Screen useful enough to use it anyway, even though it'd be a little bit faster to do the debugging stuff. However, we can definitely show dumping memory whenever we break in. So there's a couple different ways to do that. Let's get this working real quick. So ps aux grep array. I want to attach to 80814. Continue. We just got our segfault. We do x/I rip. We want to do x/gx 602020. We have not what I expected to have. Why did you not? It should have been z's. Did I forget to send buff? Yeah, I forgot to send buff. Oops. We're just going to ignore that one real quick. Pretend that one didn't happen. Pray, attach 80829, yes. Continue. Okay, let's try this again. Z's, look at that. So we now have full control of PC. So what we're going to do here, we're going to open up a new thing here. Kana, I believe we have the current libc. So I believe libc.so.6 is my libc on my local machine. I'm going to call one gadget libc.so.6. I have 3 choices of gadgets out of this 64-bit libc. And all of these are based on, wait a minute, maybe that isn't right. A 32-bit binary? No. No, this is a 64-bit binary. Why is that giving me? That must be wrong. /lib/x64 libc.so.6. So what I did here is I used LDD to tell me which libc it's trying to use when it uses this executable. I'm going to copy that locally and use that one. So now it's a 64 libc like I expect it to be. We call one gadget on it. Oh, and I give it a libc. And now we have several options. So we have these options, most of which are based off of values in RSP being null. So let's do 20gx, or let's just do 20x, just 1gx, $RSP plus 30 hex. That is not a null byte at all. 50 is the next option. That's not a null byte, but it's also not that far off. What does this thing look like? So the constraint here is not that it has to be a null byte. It has to look like valid pointers. And that looks like valid pointers to me. So our argv is going to be completely messed up because it's going to think that this is the first argument, which I guess is text, and then it's going to be a null terminated. So that gadget should work. So we should be able to take this right here. 1, 2. 2 is where I had this. So we want address to be, so one gadget is, it's a tool by David, and I forget his name, David942J. It's basically just a Ruby script to open up a libc and find occurrences of execve bin sh. It supports both the AMD 64 and the i386 stuff. Prior to finding this tool, I did this all manually. Like I'd open it up in Binary Ninja or IDA. I'd look for the calls to bin sh, I think. I'd look to references, to cross references to bin sh, and then manually go through each of them manually. Yeah, and do that. However, somebody. This David942J conveniently put together a whole bunch of stuff in order to do it automatically for you. And you can actually really easily get it all set up. It's as easy as gem install one gadget, and then it just works. Like you set that up real quick, and bam, you can now pop out these bespoke gadgets for you. So that's one gadget. But coming back over here, we want to do libc.address. And that should just work. So assuming that I know how computers work, I should be able to go enter, enter. No! That's unfortunate. That's unfortunate indeed. Okay. That's always the worst, when I think it should work and it doesn't for some unknown reason. Yes, go ahead and kill it. Continue. Enter, enter, enter. So, we SIG aborted. Why did we SIG abort? That doesn't look right at all. Ew, that doesn't look good. Okay. So I'm guessing that what this is telling me is that that address does not work. Let's try this one. So the trick with these bespoke gadgets is basically you try them until you find the one that works. And sometimes you're luckier than other times, and it's the one that I thought it would be. Other times, oh, well, this is unfortunate. So the ones that typically work are the plus 30, the plus 50, the plus 70. The other ones are a little bit harder to get working because they have actually complicated constraints. You know what? We're just going to put some bytes in here, and we're going to try this again. So we try this here. Bang ps aux grep pray. We're going to attach 80997. Yes. Continue. Enter, enter, enter. We now have our seg fault. Okay. So x/x 20gx $RSP plus 30 is this thing, which is clearly wrong. Plus 50 is this thing, which looks like a pointer. Plus 70 is this thing, which I don't have good feelings about. Yeah, that does not look like pointers at all. So I would think that the 51 would work. Because this thing, so RSP plus 10, 20, 30, 40, 50 slash 20GX. That looks like it could be an argv, but it doesn't. So let's look at the other ones. So if we use this one, RCX has to either be null or point at null. That does not look like null or point at null. So this one and this one won't work. What is R12? x/20gx, this thing. That is also not going to work. So it looks like, at least for this case, the one-shot gadgets aren't going to work. But we're not completely out of luck here. What we can do is we can just go a step farther here. So we are, if we come over here, we are currently here. So we're at the puts to call in the menu. Yeah, so in the comments, it was mentioned that you can use the search function to find binsh. What I'm using here is actually what should be a single gadget to both push binsh as an argument, well, set it as RDI as an argument, and call execve. So these are these bespoke gadgets, which if it works, because each of them has different constraints on it, if the constraints work, then this single gadget, you have to set nothing else up. All you need to do is get control flow of the program to point at this offset from the libc base, or this offset, or this offset, or this offset. But each of them has a set of constraints, so sometimes the constraints work out. A lot of the time the constraints actually work out, but not always. This is one of the cases where they clearly aren't working out. So we have puts here. So what I'm hoping for is we're trashing a ton of the heap. We called puts. What about read? So instead of crashing, so we have puts. We have the got entry for puts. Wait, what? We have fread. Where's read? Oh, it's calling read, right? I'm not crazy here. Go back. Called read. Did I? Okay. Okay. We will assume that I just can't read quite right. Although, unfortunately, read is also going to be a similar case. Oh, wait. We're also clobbering free. What am I thinking? We can do the stupid thing here, which is basically we're going to clobber this chunk here. We're going to clobber up to 18. So, where are we? Here we are. So the buffer we're going to send is going to be, so we're starting at 602.00A is where we're starting writing. And we want to go all the way up to 18. So we want to do buff is equal to, the tricky part here is we need to write some bytes. So we need to go from A, oh, right. So A to 18. So, buff is equal to A times 18 minus OXA. And this should work. What we can do here is we can actually do libc.symbols system. And what this should do is that when we go to free something, and we can get really clever here, can't we? So we're going to say this one right here is going to be /bin/sh/00. When we go to free one of these, it's going to call system instead. So if we do all of this, we're going to break in, enter here. Let's print out these 6, 7. So we want to free 7. Yay, we have a shell. So what we did here is we just basically remapped the free function in the GOT to be system instead, and then we freed something which was /bin/sh. And that's it. That's how we landed all of this. So, got a little bit of time here. So one of the guys in the chat asked about setting up some of the dumping stuff as we step through a program. And there's a couple different ways to do this. So you can do things like, I want to display every time. So display will do, let's actually type this real quick. So help display. What this is going to do is it's going to print the value of an expression every time the program stops. So I don't remember if I can do this. No, I can't. But I can do things like I want to display every time that we step, I want to see what the current program counter is. So we just broke in here. And what this is doing is it's saying every time that we would get this little GDB console, I want to run x/I rip. And it's going to print out what the current instruction is. Or I could do, I want to do 20 bytes at RSP. So I would do disp that. And so if I restart it, I break in, it's going to print out, I've now registered 2 different things to display. So it's going to give me the current instruction and some bytes of the stack. And I can set up things like that to work that way. There's also GDB breakpoint commands. And I always have to look up how these work because I don't quite use them often enough to matter. Basically, you can set up a set of commands to run for a given breakpoint, which can include continuing from that breakpoint. Yeah, so here's actually an example of that. So we want to break on foo. We then want to set up some commands that basically we want this in particular is setting up some basic instrumentation as this example. When every time foo is called, they want to break every, so sorry, I'm going to walk through what this example does. So break on foo if whatever the x variable is greater than 0. Then we're going to set up some commands for that to first be silent. I'm not quite sure what silent does, but that's not that important. But when it is, it's going to use printf to print out the value of x and then continue. And all we've done here is this set up some basic instrumentation for whenever foo gets called. So for example, you could do break malloc commands silent, printf malloc %x, and then comma %RDI, continue, end. And then when we run this, we actually get here nicely instrumented all of our calls to malloc. Not quite sure why some of these sizes are kind of odd like that. Yeah, that's the basics of it. So we set up this, let's say we want to allocate 50 bytes. We just see the call to malloc. Ideally, I would have put in like a new line there so it prints it out a little more cleanly, but that's one of the ways to do some of the instrumentation stuff. Like you can set up some pretty clean instrumentation that way, that every time I hit a malloc or a free, I want to print out what that malloc or free was called with. It's a lot easier to do on x64 because you're passing those arguments in registers. But you can set it up with some more trickery with, can I see the returned address of malloc buffers? Not with what I'm doing here, but I can do, so undisp2, undisp1. I want to delete all of my breakpoints. I want to break on malloc. I'm going to do commands silent printf malloc %x is equal to comma $RDI. So it's going to print out the value of RDI. I then want to do fin, so I want to run until malloc returns printf ox %x. Yeah, let's just do it this way. /n, oh, I'm sorry, space ox %x /n, comma, rax, because rax is going to continue the contain the return address, because now we're at the end of this function. Continue, and then it's end, right? Yeah, end. So if we do this again, oh no! What happened? Oh, did printf not work? No, that should have worked fine. Oh, no, that totally worked, didn't it? It's printing out extra information for us because of when fin returns, it's actually returning out some information. I'm not sure how to suppress this. I want to delete all of my breakpoints. I want to break malloc commands silent printf malloc %x is equal to comma RDI. I want to fin. So fin should work. I want to printf ox %x rax continue end. No. So unfortunately, the problem here is using fin isn't working quite the way that I would like it to, because fin is breaking in, I guess because it didn't know where we were. No, that's not what I want. I'll have to take a look at it. I have done it before. I've definitely done where individual calls to malloc I want to instrument. I can do that. Um, Unfortunately, doing all of them is a little trickier. One of the ways to do it is I want to delete all my breakpoints. I want to break on malloc commands silent printf malloc percent x is equal to RDI continue end. And now I can do break on where are we here? In this case, there's only one time we're calling malloc. So I can break here, 400 B24. Oh, no, I want star 400 B24, continue. Oops, that is not what I want to do. I want commands 5, silent printf ox percent x slash n rax n. Oh, let's try this again. Commands 5, silent printf. Yeah, there's some flag to make it not do that, and I just don't know what it is off the top of my head. So if we do this again, when we actually call printf, when we call it from where we wanted to, it's going to print it out. When it gets called anywhere else, it doesn't print out the return address. But this time, we actually get the return address like this. So this is one way to do it. I'm sure there are other ways that are probably a little bit cleaner than what I'm doing here, because honestly, like setting it up that way is kind of messy. There's got to be some like option for Fin that works better. I'll take a look at it, and on Wednesday, if I find something, I will definitely let you know. But I think it's about everything that I have for tonight. The short version is we went through most of the ponables from ASIS CTF. We did start and start hard, which were just basic prop chain attacks. CRC, which was setting up a ROP chain with an information disclosure to leak out a cookie. And at least the way that I did it, the information disclosure was using the CRC of memory addresses to get that cookie value and read out arbitrary memory. And then Fulang, which was a like emulator / programming language with some memory, an interpreter for that, where you were able to get the pointer into memory where we currently were to point at the register that holds that pointer, mess with that, do all sorts of terrible things. So those were the 4 ponables that I landed during the competition, when I think I spent about the first hour running through the CTFs that are currently ongoing, which are Pico CTF and Fit CTF, both of which are good if you are looking for low difficulty challenges. Like I would say, so I looked at Fit CTF on Sunday, and I'd say there's probably nothing in the competition that it would be less than about a 200 point value on the standard point value scale. And Pico CTF I haven't looked at this year's, but it's designed for middle and high school students, so the difficulty is usually pretty low. And that's good. It's a good chance to practice, plus it's running, both of those are running through the end of this week. So if you want something to do in one of the evenings or, on your lunch break or something, take a look at either of those, knock a couple of challenges around, have some fun with those. And this weekend is BCTF, which is run by Blue Lotus. Should be a ton of fun. I'm really looking forward to it. But that was the first chunk of time, was going through all that. Then we talked about the challenges that I solved during the competition. And then we spent basically the past hour and a half now going through how to land Kanak MGF. The first version is what we landed here. The second version, you could use the same technique on. It's just instead of using the GOT, we would have to use something out of libc. And we can't use the pray for Allah thing to get out the ASLR values. We would have to actually use the stale pointers, I think, to calculate where we would be. But I think we should be able to do the same thing and overwrite like the free hook immediately prior to it. So the basic technique there would be, if we pull up our pictures here, let's pull up a new one so we can actually tell what we're doing. I haven't verified this because I haven't actually landed it yet, but if we allocate a buffer, we free it, the first two D words, so the first quad word is the previous size, the next quad word is the size of the current buffer, this quad word is a forward pointer, and this is a back pointer. If you're in the normal bins section of the free list. If you're in the fast bins, it only uses this one, but we talked about that plenty. So to solve the harder version of Kanak MGF, I would use these two pointers to know where main arena is, and then I can walk backwards from that to figure out where the free hook is. I believe it's the free hook that comes before. One of the two, the free hook or the malloc hook, occurs prior to main arena, and one of them happens after, and I have to look up every time which one's which. But basically, use these two pointers into, sorry, I'm spacing here for a second, into main arena, because, so basically, allocate this big thing, free it, and then use the read functionality to print out what this pointer is. We now have a pointer into main arena. Use that to calculate where the free hook or malloc hook is, and then use the exact same technique with the fast bins to get a region just prior to the malloc or free hook, bash that, and do the same type of exploitation we did here. That's the way I would go about solving it. I haven't verified that that's a way to actually solve it, but that's the way I would do it. And I think that's basically all the ponables. So there are two that we didn't cover here. One of which was, what's it called? You're going to come up with my search here. No, I do not mean ASAN. If we remember previously, apparently Google thinks that when I say ASAN, I mean the Autism Spectrum Awareness Network. But the other challenges that I did not go over here were random generator, which was another stack buffer overflow with a ROP chain that you had to generate, except it was very constrained with the bytes you could use. I'm not entirely sure what the trick was for this. I suspect it was something like there was a pointer leak or something that I wasn't aware of, or the constraints on the gadgets were much lower than I thought they were. There was also defaulter, which according to the description, you gave it some shellcode and it would run it or something. So if you netcatted to this thing, it said something about accepting shellcode, you sent it some bytes and it did the thing. I didn't actually get very far with this because I didn't actually know what it was doing, so I kind of just gave up. I figured, at least my thoughts on it were that I was going to complete these 3 challenges first, and then if I still had time, come back and do this. And clearly, I never even finished these 3, so I never got around to it. But that's the short description of the ponables from ASIS CTF. I would say I thought they were pretty decent, especially the CRC one I liked, and I liked the Fulang quite a bit. Like, I liked those challenges quite a bit. I wasn't a huge fan of start and start hard because I'm not a fan of the really simple challenges that have some trick you have to get. And both of these were just, we read some bytes onto the stack. The same with random generator. We read some bytes onto the stack. And while I understand the value of having those in that they are very straightforward and they're very good for learning from, they're not as much fun to solve. And personally, when I'm going to play CTF, I'm playing because I want challenges that I think are fun to solve. And simple ROP chains aren't all that fun to solve. Kanak MGF, though, was quite a bit more interesting, and I have been kicking myself for the past 36 hours now for not having remembered that I could use a misaligned pointer to get that size for a fast bin. So, like always, everybody, if you have any questions, let me know. I should be available on Twitter. That's probably the easiest way to get a hold of me, or leave a comment on the video. Other than that, I will see people on Wednesday. We're going to be looking at PDF Crack again, which is some PDF cracking software. We're going to try and find some zero-day bugs in that thing and try and land. Well, we already found some last week's Wednesday stream. This week, we're going to try and actually land them. And then, depending on how much time that takes, we're going to start looking at Python as a source of memory corruption. So if you're interested, tune into that on Wednesday. And then finally, next weekend, I'm gone. So next Monday and Wednesday, which is the 17th and 19th, I am out of town and away from the internet and will not be streaming. So the next CTF stream will be the 24th, where I'll get to talk about BCTF and Plaid CTF, which are the weekends of the 15th and 22nd. And we're going to get ready for DEF CON Quals, which is the final weekend. So the next 3 weekends, tons of good hard CTFs. There should be tons of ponables to talk about on Monday. So we'll see how things go. And thanks everybody for tuning in. Again, any questions, comments, things like that? Comments on the video or send me a message on Twitter are probably the easiest ways to get a hold of me. Thanks everybody. Bye.